So let's do another example, which has jets in it, and we'll see what the similarities are to this SCET2 setup in terms of just identifying still what the right degrees of freedom are. So let's look at E plus E minus to 2 jets. So E plus E minus collide. They produce a virtual photon, say. The virtual photon produces a quark-antiquark pair. The quark-antiquark pair starts to radiate, and we get jets, just 2 of them. So again, there's a kind of natural frame to describe the scattering, and that's the center of mass frame of the E plus E minus. Most E plus E minus colliders are built in that frame. And if you're in the center of mass frame, and you call the form momentum of this photon Q, then it just has an energy component. So Q here is not the same as the Q in our previous example, but we're always going to identify the hard scale as Q. So here the hard scale is the scale of the energy of the collision in the center of mass frame. And if you ask what does the event look like in the center of mass frame, then these 2 jets which are going out have to balance each other. And so you have 2 back-to-back jets. So we draw it like this. One jet going this way, one jet going that way. Our original E plus E minus might have come in from some other direction, so maybe E plus E minus were coming in from here and here. And then we have these 2 jets going out this way. Since they're jets, that means they're collimated sprays of radiation. So they're not featureless. They have some size to them, like this. And in this process, we can quickly identify that there's 2 relevant directions. It's back to back, but let's define this direction of this jet to be n1, some light-like vector that points in that direction, and this one to be n2. So generically, we could say that n is some 1 n hat. And if we choose this to be the z-axis, then this just be 1, 0, 0, 1, just like we had before. But we can always pick a light-like vector that points along some direction n hat. So when I draw a picture like this, really what I mean when I say n1 points in this direction is that the hat part of it points in that direction in 3 space. OK, so just like before, what happens with a jet is, as I said last time actually, we have a large energy flow in this direction and a smaller perpendicular flow. So if we measure perpendicular momentum, which you can think of as perpendicular to that axis, 3-axis, then that's the perpendicular flow inside the jet. And so that's, if we actually want to talk about constituents inside the jet, then we'll be interested in smaller perpendicular flow than flow in the forward direction, and that's what makes it into a collimated jet. You have a question? Sure.
So you're not using anything about the QCD matrix elements to tell you that things is squashed. You're just saying, okay, notice that we have a squashed object.
Yeah, that's the attitude. Right. So I mean, we'll see why. You can ask the question, why do we get jets in the first place? And we haven't talked about that. And we could talk about that. I'm taking the attitude here. This is what we observe. How do we design an effective field theory for it? And we'll see then, from that effective theory, we can go back and understand why it is that we get these objects and why actually, when you look at cross sections, that this is the leading order description of what happens. But we'll come to that later. Good question. Any other questions? All right. Yeah, in the hadron case, it's a little, you just say this process exists. And I didn't explain to you why the process could exist. But in the jet case, there's some more dynamics going into the fact that the process exists. The fact that QCD likes to radiate collinear to a direction, which has to do with the infrared structure of the theory. And we'll come back to that. short answer, of course, is that things like to radiate in that direction because there's large logarithms that enhance splittings that are collinear to the direction of motion. And you also get smaller coupling constants when you do that, rather than a wide-angle emission. So we're saying here, what we're saying is we measure E plus E minus to 2 jets. If I had an extra wide-angle emission, that would be E plus E minus to 3 jets. So that I ruled that out just right at the beginning. OK, so what you can do with this picture in order to define what's going on is you can say, well, they're back-to-back jets. Let's draw a hemisphere. So this is supposed to be kind of out of the board, pointing at you. Let's draw a hemisphere between these two, and then we can call one side A and the other side B. And we can talk about momenta that are flowing in the A hemisphere and the B hemisphere, and you see that we have one jet in each hemisphere. So we have a jet of hadrons in hemisphere A. And we have another one in hemisphere B. So in some ways, we can talk about A and B independently. So let's start off by talking about A, which is what I call the N1 collinear jet. And if we ask about constituents in the jet, then the perpendicular momentum will be of some size, which let me just call it delta. And that'll be much smaller than P minus, which is of size Q. So the energy that we pump in through the photon has to leave, and the only place that it can leave is that half of it has to kind of leave this direction, half of it has to leave that direction by energy conservation. And so we have a large energy flow along in the P minus component, and then we have a much smaller amount in the P perp, and that's what I already said. And given those two facts, you can ask, what about the constituents of the jet? And again, they're collinear, because you have a hierarchy. So the plus, minus, and perpendicular momentum of constituents would scale in that way. And that is Q lambda squared 1 lambda, just as before, with a different lambda. So here, lambda is how much spread in perp do we have over Q. And this delta doesn't have to be lambda QCD. It could be something much bigger. Another way of thinking about physically what this delta is to calculate something called the jet mass. So you could define the mass of the jet as the sum of the 4 vectors in hemisphere A of all the particles squared. And if you ask about how big that is, if in these coordinates that we're using, it's P plus times P minus, minus P perp squared. If we align things so that this thing is really aligned with the jet, there won't be any P perp squared. But that wouldn't change a scaling argument anyway. So basically, this is, if you ask about what this jet mass is, it's scaling like a P plus times a P minus. And it's scaling like delta squared. So the jet mass is something of order delta squared, and that's much less than Q squared. So another way of characterizing that you have a jet is to measure the invariant mass of all the particles in this hemisphere. And if that invariant mass is small relative to the hard scale, then it's collimated. Okay, so mj squared over q squared much less than 1 also means collimated. So we could talk about it either in terms of perpendicular spread, or we could talk about it as an invariant mass. Okay. This is much less than 1. Now, you could ask with this delta, we didn't specify what it is. So what are possible values of delta? Well, let's first talk about what it's not. If delta was of order q, then obviously we'd break the kind of scaling that we have here, that this should be much less than 1. And what happens in that case is we don't have dijets. So if either the mass mj squared of the particles becomes of order q squared, or the perpendicular spread becomes of order q, then we don't have dijets anymore. And basically, in this case, you would be talking about inclusive sum over jets. And that would be something that you would actually describe in a different way in the effective field theory, because you wouldn't then have collinear degrees of freedom for this jet. It's really picking out the dijet process that means that these collinear degrees of freedom are relevant. If you did just E plus E minus to hadrons, that's something you could do with an operator product expansion without ever talking about SCET. And that would be valid if you were really doing an inclusive sum over jets in all directions without any restrictions that tell you it's a dijet. And then the effective power counting in your OPE would be such that delta is of order q. So this is actually the OPE region. Let me call it the OPE region of Peskin, or any other field theory book. Another thing we could do is we could take delta to be very small. We could take delta all the way down to lambda QCD. And that's also not a jet. If delta is of order lambda QCD, what happens with the spray of radiation is that it gets bound into a hadron. It just can't separate. Confinement grabs it, and you get an energetic hadron, not a jet. So if the jets get too narrow, in particular this narrow, then the constituents are bound into a hadron. And that might be something you want to talk about, but it wouldn't be talking about E plus E minus to dijets. You'd be talking about E plus E minus to pi plus pi minus or something. And then you'd actually use this other SCET that we were talking about a moment ago, not the one for jets. OK, so anything kind of in between these two regions, much greater than lambda QCD, much less than q, then we can talk about it as being jets. OK. So we figure out what region we're interested in by figuring out what region we're not interested in. So that was one jet. And kind of by symmetry, we can talk about the other one. So there's this one that I called N2. The simplest way of invoking symmetry is to take N1 to point along N, which is our, say, 1, 0, 0, minus 1, and then just take N2 to be N bar, which is 1, 0, 0, plus 1. And then the description of the N2 jet is the same as the description of the N1 jet. It's just you switch pluses and minuses. Remember that what defines plus and minus depends on the choice of this N bar. A priori, that choice of N bar has nothing to do with N2, and this is just a different physical vector. Both N1 and N2 are physical. N bar is an auxiliary vector, but if I just happen to choose that N2 is equal to that auxiliary vector, then it makes things simple, because we just have a relation between the two sets of degrees of freedom that's swapping pluses and minuses. OK. So that's actually not the end of the story of the degrees of freedom here. And that is because even if we make restrictions to get these dijets, we can still have soft radiation that is between the jets. And so this one's a little less intuitive, perhaps. So I'll call these guys ultrasoft modes. I'll label them by US for ultrasoft. And one way of thinking about physically what they're doing is that they're allowing you to communicate between the jets. There can be radiation that's radiated from one jet that interferes with the other jet. This is a homogeneous type of radiation, so it has the same scaling in the plus, minus, and perp. And if I look and I compare this to the, so this is for these ultrasoft modes. If I compare this to the scaling that we have for, the, say, the n collinear modes, so let me call that Pn, that was delta squared over q, q delta. And if I make the mirror for the other jet, then I would switch these two, delta squared over q, delta. So when I say communicate, what I mean is that these guys can talk to both of these guys without interfering with their scaling. So if they're not going to interfere with this guy's scaling, they better have plus momentum that's the same size. If it was any bigger, then we'd have a problem because they'd interfere with this scaling when they tried to communicate. And then likewise for the minus, they better have scaling of the same size, and then perp is fixed. So the word communicate here, in the way I'm defining it, means sharing momenta of a common size. Well, it means sharing momenta and not taking the other particle off shell. OK, so we can draw a picture for this one, too. Like we have our SCET2 picture, we could draw an SCET1 picture, and that helps to make pictures always help to make words more palatable or absorbable. So same type of picture where we have P minus and P plus. We also can think about things in terms of hyperbola of constant invariant mass. We now have some collinear modes for the n1 direction. There's going to be some purple collinear modes for the n2 direction. There's going to be these soft modes. And then we could also have some hard modes that we want to integrate out. So these are the ultrasoft modes. So the reason that I call them ultrasoft rather than soft is because by soft we meant something that sat on the same hyperbola. And here it sits on a lower hyperbola, so it should be softer, so we call it ultrasoft. This is the hyperbola where p squared is of order delta squared. This is the hyperbola where p squared is of order delta 4 over q squared. If you square any one of these guys, you get delta 4 over q squared. And up here is p squared over q squared. And this kind of thing is called SCET1. So what does it mean to communicate? Well, it means that there's two momenta that are the same size. So the fact that I tried to line these up as best I could, partially succeeding, is what I mean by communicate. These things are the same size in the plus, these things are the same size in the minus. And if we want to put in kind of how big these things are, we would say that. So the scaling of the ultrasoft, unlike the scaling of the ultrasoft in all components scales like lambda squared. So in terms of scaling parameters, we would say that it goes like this. And here we're not talking about soft. It would have lambda in all components. So this is the effective theory that turns out to be the right one for jets. And whenever you have this kind of situation where you've got collinear modes that are living on a higher hyperbola than the soft modes, which you call ultrasoft modes, that's an SCET1 type theory. And these two actually cover a wide range of phenomenology, these two particular cases, SCET1 and SCET2. OK, questions? Talk a little bit more about this picture.
Should you think of the soft nodes as being smaller than or equal to lambda squared?
Yeah, so that's right. So you can ask now, how should I think about drawing the blobs around these things, right? And you still should think about these things with blobs like that. But then there becomes a question for sort of with the, which we didn't have, which was kind of more obvious actually in the SCET1 case. And that is kind of how these things overlap with the axes. And we'll come back and talk about that later. But I think for now, just think of them as being localized in that way. And so the softs, in the case of the softs in the collinear we had before, you can think of them as uniformly kind of coming down into the infrared. Here it's not like that because this guy is more infrared to begin with. And that will have some impact later on. OK. So what are the important features here? Well, we see this idea that I mentioned would occur, that we have multiple modes for the infrared. And you could try to get away with not doing that, but then you would have a lot of trouble with your power counting. And since power counting, as I've convinced you, hopefully by now, is just as important as other things when you're designing an effective theory, you really don't want to mess with that. And so you're forced into a situation where you start talking about having multiple fields for the same degrees of freedom, because the scaling of the momentum in different regions of the space you're interested in is just different. So the derivatives that are corresponding to those momenta are going to scale differently. And if that's the case, you're going to need to have multiple fields to describe those different regions. We'll also see that the power counting is different. So you can ask, what are you integrating out? And we're still taking the attitude that we integrate out modes that are off shell. And so above a given hyperbola. So that part of our story of effective field theory is really the same. It's just that when we describe the low energy modes, we need more than one of them. So what we mean by off-shell is the same as it always has meant. Off-shell modes get integrated out. Those are modes with large p squared. like the hard modes. So one natural question when you're talking about these effective field theories is, well, how do I know I have all the modes? And that's a good question. And there's been examples in the literature where people wrote papers where they didn't have all the modes, and modes were missing. So it's not even an academic question. It's really a pitfall in some sense that you can fall into. So I take the following attitude towards that question. You should attack it from all sides. So one is that you should really physically think about what the modes are doing and have a physical description of why those modes are something relevant for your effective field theory. After all, your effective field theory is supposed to be description of nature and infrared physics. So there should be something physical associated to what those modes are doing. That's the physics side. Calculationally, there's various ways that you could approach this. So one thing you can do, which is sort of an order by order thing, is you can just calculate results at one loop and make sure you match up infrared divergences. Because if you don't match up the infrared divergences, then you know you're missing some infrared degree of freedom in the effective field theory. Okay, so that's a very kind of one way you can check for the modes. So you can either do physics, or you could calculate. And when you calculate, there's also something called the method of regions, which is a nice way of thinking about trying to discover modes, which basically says that any full theory calculation I could do that calculation by dividing up the integrand into regions. And if I'm using dimensional regularization, then the full theory answer is just the sum over regions. So you can just calculate using some EFT as I described to you and check it. Or you could do it a different way. You could say calculate the full theory result with something called the method of regions. And that's just a way of calculating the full theory result. But it's a way of telling you what regions are important. There's also things that there's all order theorems in QCD about what regions can give infrared divergences. And that's another thing you can use. And I won't talk about this last one, or actually about this one. So these are different ways that you could look for what are the relevant degrees of freedom. And actually, when we started doing SCET, we didn't separate between ultrasoft and soft. We had both of them at the same time. And the reason was we knew that in some examples we needed soft, in some examples we needed ultrasoft. And we were thinking of it as one theory, not this SCET1 and SCET2. And then at some point we realized that all the examples we were doing, as we did more and more examples, they broke into these two categories, one for jets, one for hadrons. And so we were finding that, for example, if you add a soft mode to this picture, it just ends up being totally irrelevant, and you can just absorb it or remove it. You don't need it. And likewise, if you tried to put an ultrasoft mode into the example of energetic hadrons, you'd find you don't need it. So you could put too many degrees of freedom in as well. It's not just that you could have too few. You could actually try to put more than you need, and then you would see from your calculations that you actually had more than you need. But in some sense, this is the reason I'm spending time on this is because this is in some sense the tricky part. Once we know what the modes are, we'll just get the effective field theory and go.
Is the second point here, the method of regions, like check the full theory, is that any different than the check it of the first point?
Yeah, because here what I'm saying is hypothesize some effective field theory.
But check it against the full theory.
And then check it against the full theory. And so the direction here is that you write down something and you do calculations in two theories and you make sure they agree. Here it's a little bit different because there may not be a one-to-one correspondence of the modes of the method of regions. Method of regions is not technically exactly what the effective theory is. So this can give you hints about what the effective theory is. Then you basically go back and do this, but sort of helps you because you have most of the calculations to do this. Yeah. So technically they're a little bit different, but they're pretty related. Okay. So in the example we had here, it was a little more complicated than our beta d pi example because we had 3 things in the infrared. And you could ask the question, is there something with just one jet? The reason we had 3 things is because we had 2 jets. We had the purple jet and the pink jet. And we can come up with a process with only 1 jet. So let me give you a third example. If we have something recoiling against the jet that's electromagnetic, like a photon, then we could just have 1 jet. So one way of doing that is to look at a process like b dash gamma, where you say that really what you want is b to 1 jet plus a photon. And that's a region of phase space in b dash gamma, where the picture over there just has 1 jet. And so it's the same picture, but now we just have our pink jet. So the right modes for this picture, for this process in the region where you just have 1 jet, would be like this, where this is hard and you integrate it out, and you just have 2 things in the infrared, a CN and an ultrasoft. In this case, you also have to ask the question, what is the hadronic process? Well, it has a B meson. What are the things inside the B meson that are binding it together? And you would make those the ultrasoft modes. So in this process here, it's very natural to take p squared of this lowest line to be lambda QCD squared. And then these guys are binding the B meson. They're the soft modes of the B meson. This collinear hyperbola for the jet lives somewhere between, and this here, in this case, would be something of order the B quark mass squared. Okay? So it's a little bit different than over here, where there was kind of a no natural, this thing was set by the kind of what we chose to do with the jets was setting this. Here, there's kind of a natural scale so where you know that there's going to be some degrees of freedom, and so it's very natural in this case to take that as an input. And then you could actually figure out, given that, what the jets should be. And the jets would have lambda QCD times MB, which is in the middle. So that's kind of a natural scaling for the B dash gamma process. Okay, so just to give you an idea how, if I have a jet, it's going to look something like this. It might not look exactly like that. It depends on how many jets you have. And of course, these pictures actually get more complicated if you try to start drawing them when you have 3 jets, because then the plane is no longer enough.